Hello, everyone. My name is Alexis King. I'm from Northwestern University, and today I'm going to be talking to you about a programming language that I've been working on for the past 2 years or so in my spare time. And just as a brief disclaimer before I get started, the language is very much a work in progress, so I don't recommend that at the end of this talk you all go home and rewrite all your programs in Hackett. But it is to a point where now I can kind of show off some of the ideas behind it, show you a couple of small programs and some of the things that it can do. So before I get started, I want to give you just a little bit of context about sort of where this language came from, because obviously there's a lot of programming languages that exist. And I've used a lot of programming languages, but two really stood out to me in my short time writing programs. And the first of those is Haskell. I wrote Haskell for 2 years professionally. It's a pure functional statically typed programming language. There's a number of talks here talking about Haskell, so if you want to learn more about it, you probably can. I'm not going to spend too much time talking about Haskell, but it is a really pleasant programming language. The other one is a language called Racket, which is totally different, and it's actually a little bit difficult to explain. It's a lot of different things. But the main thing that people think of when they hear about Racket is a scheme descendant. It's a dynamically typed Lisp, which is obviously completely different from Haskell. But the thing that it's most known for is its really, really robust state-of-the-art macro system. And so what would happen is when I was writing programs in Haskell, I would find myself wanting to have the macro system in Racket, and when I was writing Racket, I would want to have the nice type system from Haskell. So I said, well, why do I have to pick just one? Why can I not put them together and make a new programming language? So that's sort of what Hackett is about, and I'm going to explain over the course of this talk why I think that essentially Haskell deserves a macro system and why specifically it deserves Racket's macro system. But I'm also going to talk about something else, which is maybe if you're already sold on macro systems, if you've already used Lisp-like languages before and you think that they're great, then I'm going to try and sell you on why I think that macro systems can benefit from a type system in a way that actually hasn't really been done before, at least not to the extent that I think it could be. So before I get into those two things and explain all of what I'm talking about, I want to give you just a really quick peek at what some actual Hackett code looks like today. So here I have a Hackett program. Hopefully you can see that. And it's not a very exciting Hackett program. It's very short. It's about 30 lines long, and it implements a RESTful web server, which again is not super exciting. But I can run this program, and I get a server running on port 8080. And just to demonstrate that it does in fact work, I can say hello, strange loop 2018, and there we go. It says hello, strange loop 2018. The server can also do a couple of other really simple things. It can add two numbers together. So I can go in here and I can say add 1 to 2, and it gets back 3. Again, this is obviously going to be an extremely popular web service. And if I put in some nonsense in here, like something that's not a number, I get back a nice error message. And it can also do things like calculate the distance between 2 points, also something extremely important. So I can say distance between 1, 2, or actually it's distance from 1, 2 to 3, 4, and I get back some floating point number. So again, the program itself is not very exciting, or at least what it does isn't very exciting. What's exciting is the program itself. So to demonstrate that this is, in fact, a statically typed programming language, even though it has all these Lispy parentheses, I'm going to hover over some of these identifiers, and you can see that I get some type tooltips. So this has a function, which isn't very interesting because the function's name is integer to double, and its type is integer to double. But if we look at something a little bit more exciting, like greet, this is a function I define inside this module. It has the type string to string. This number here has type integer. And indeed, if I change this to a string, then you probably can't see it very well, but this little dot in the corner turns red, and there's a message at the bottom that says type mismatch between string and integer, and indeed it highlights that part right there, because that's the location of the type error. So that's happening at compile time. It is statically typed. And in addition to that, there's a few different things in this program. There's a really simple function definition. There's a data type definition. There's some pattern matching. And there's also this def server thing, which actually defines in sort of a declarative way what the web server is. So it has 3 routes. It has that hello route, add, distance from, and there's sort of a declarative specification about what data types it takes and returns, and then what function it ends up calling. So I'm going to go into parts of this program in a little bit more detail. I'm going to go back into the slides. But the first thing I want to show you is that Hackett really is fundamentally a Haskell first and foremost. It looks probably not all that much like a Haskell. Again, it has all those lispy parentheses, but if you look past them, it really is almost identical to the equivalent Haskell syntax. So if you look at, for example, the definition of a data type in Hackett and a definition of the same data type in Haskell, again, more parentheses on the top, but otherwise it looks essentially the same. The same thing is true for pattern matching. Again, on the top with Hackett, on the bottom with Haskell. Some do notation, like Haskell, Hackett has a monadic interface to I/O, and if you don't know what that means, that's OK. It's not important for this talk, but if you do, it's a little interesting. And type class definitions. So again, Hackett on the top, Haskell on the bottom looks very, very similar. So Hackett is a Haskell first and foremost, and if you are familiar with Haskell, once you get past the syntax, you'll feel right at home writing Hackett programs. But of course, it's not just Haskell, because if it was, then this would be a pretty boring talk. So there's also this def server thing, and this does not correspond to any feature in Haskell, which is probably a good thing, because it would be weird if Haskell, as a general purpose programming language, had a language feature for defining RESTful web services. And this indeed is a macro, and I defined it in a little library that I just implemented for demos and this talk. So what is a macro? If you're not familiar with a macro, then I'll give you a really quick crash course in what a macro is. A macro is just the idea of we want to add a new feature to our programming language, something that we can't define just as an ordinary function. So this def server thing has sort of a custom syntax. It defines a function, called in this case run server. We can't implement that as a function. So what we'll do is we'll define a translation from some new language feature into some simpler constructs that are already in our language. In this case, just ordinary function definition, function calls, pattern matching. And we do that just by writing an ordinary function, an ordinary pure function, from a syntax tree to a new syntax tree. And we just do that in our programming language. And importantly, this function is defined and executed at compile time. So the compiler will find all the cases of macros in our program, it'll run the associated functions that we defined, and then eventually we'll get a program that doesn't have any macros in it, and we can send that off to the compiler, and it works traditionally. So this is what a macro is. That's really all that a macro is. There's more complexities if you get into the details, but that's really essentially the gist of it. So macros allow us to abstract over syntax, and that's what's interesting about macros. Because they run at compile time, they let us abstract over things that ordinary functions do not. And so oftentimes, I sometimes hear people say, well, Haskell doesn't need macros because of some reason or another. But I'm going to make the case that Haskell does need macros, and indeed, Haskellers are asking for macros. They don't know that that's what they're asking for, but that's what they're asking for. So this def server example is one example of a DSL that can be implemented using macros. I don't expect you to read this. This is a comment that I found on Reddit about a year ago, the r/Haskell subreddit, where somebody's saying, hey, I have this code, I've translated it into Hackett syntax so that I can show some things off. But otherwise, this is essentially what they were saying. I have this pattern. I keep repeating this pattern matching over and over again, and I can't abstract this into a function because patterns in Haskell are not first class. So you might say, well, maybe we could contort this code to use lenses, refactor some things, but with macros, it's very easy. You can just define a custom syntax that I have this pattern that happens to be in my code. I'll define a tiny little macro for it, and then I can abstract over it and change it in one place if I decide to change it at some point. And indeed, this macro is very simple to write. It's just a few lines of code in Hackett. So that's one example. If you have sort of this boilerplate that you can't abstract easily, you can abstract over it with macros. Another thing that you can do is, this is an example that somebody posted in a blog post also about a year ago, where they wrote these two functions, and these are two functions that take booleans as a first argument. And importantly, it turns out that these two functions are mutually recursive, and the only place the boolean is actually used is right there. It's being used with that if expression. But because these two functions are mutually recursive, then the Boolean has to be threaded around everywhere. And it makes the code really messy and difficult to understand because there's all this extraneous information. So the author of this blog post said, wouldn't it be awesome if we could add a feature to Haskell called this section thing, where we could say everything in the section just sort of implicitly has access to this additional parameter. And outside the section form, they just act like functions with extra parameters. But inside the section form, it's just sort of implicitly passed around. And somebody on the subreddit, again, said, actually, it turns out that we can implement this in terms of existing Haskell features, which is really cool, but there's a little bit of boilerplate. And so the author of the blog post said, wouldn't it be awesome if we could get rid of that boilerplate? And indeed, with a tiny little macro in Hackett, you can. So this is really cool because it means that macros allow us to do a bunch of different things that we can't do in Haskell natively. Haskellers are asking for them. Specifically, they allow us to abstract over syntax. They give us DSLs, like that def server thing. They let us eliminate boilerplate. They let us actually add features to the language without having to change the compiler, just as a library. And Haskell programmers want them. So hopefully, at this point in the talk, I have convinced you that macros are useful things that maybe you should want to use in your programs. But now I sort of want to explain how can macros themselves benefit from Haskell? If you're already a list programmer or you've used list macros before, how can the combination of these things be greater than the sum of their parts? So what I want to discuss is, it turns out that the title of my talk is actually a little bit of a lie. It's a little bit misleading. The title of my talk was that Hackett is a metaprogrammable Haskell, but there's a secret, and that secret is that Haskell's actually already really good at metaprogramming. If you used Haskell, there's all kinds of DSLs that exist already that are in widespread use by the community. One of them, for example, is megaparsec. It's a parser combinator library. It's a DSL for writing parsers. There's a DSL called opt_parse_applicative for handling command line arguments. There's a DSL for creating HTML. And the one that I find the most impressive is this DSL called servant. Now, what servant is actually very similar to the example at the beginning of my talk, which is a little DSL for defining RESTful web services. So the way servant works is you start by basically describing your API, your RESTful API, as a type. Now, this is kind of difficult to read and write. There's a steep learning curve, but that actually does represent a RESTful API. So once you get over that, and once you can figure out how to write that type down, then all you have to do is write a couple of functions on your data types, and you write a tiny little bit of glue to glue the type and your functions together, and you get a RESTful web server out of it. And that's amazing. How is it that in just a handful, just a few lines of code, we were able to get a RESTful web server without the macros that I was talking about earlier? So there's clearly some kind of code generation going on here. There's something macro-like going on here, despite the fact that we weren't able to define a nice new syntax for it. It's not maybe as nice, but there's something really interesting happening here. So the secret sauce to all of this is type classes. So type classes are a feature of Haskell, and if you're not familiar with them, that's also OK. I'm going to explain what they mean. The basic idea of type classes is that type classes are a mechanism for function overloading, for saying that if I apply this map function to a list, then it applies add1 to all the elements of the list. But if I apply it to an optional, then it applies it to the value inside the optional, and it just gives me back nothing if there's nothing there. So fundamentally, this is not super exciting. It doesn't seem like it would have anything to do with metaprogramming. If you're a C++ programmer, you might see where I'm going. But if you're not, then it turns out, though, that Haskell's support for operator overloading is much, much more powerful than in, say, Java or some other programming language that you might be familiar with. And so, for example, it can be used to overload ordinary values, not just functions. So, for example, this empty value is defined with a type class. And so when we say, I want to use empty as a list, then we get back the empty list. And if I want to use it as an optional, then I get back nothing. So this is something that you can't really do in other programming languages. But again, it doesn't really seem like it has that much to do with metaprogramming. So in order to understand the connection, we have to think about what it actually means to evaluate a program in Haskell. What does it mean to evaluate empty? And the answer is that we actually don't know, because we don't know what type empty has at this point. So once we give it a type, like saying, I want it to be an optional, now we know what this program will evaluate to. But this is really interesting, because it means that the evaluation of programs in Haskell depends on their types. Now, this might seem totally obvious. Of course it depends on their types, but it's actually not obvious. If you think of a lot of other programming languages, real programming languages, they usually implement type erasure. So if we take a look at this, this is some flow code, which is gradually typed JavaScript. And it has some type annotations. And clearly, the flow type checker is going to make sure that the types are correct. But once it does that, it throws the types away, and you just get an ordinary JavaScript program. So in that sense, in most programming languages, types are mostly only used for validation. And I think that that's a little disappointing, because one, there's a lot of information in the types. The compiler knows a lot about my program. And I have to sort of contort my program at times to satisfy the type checker. Why can I not get more back in return than just some basic validation? And so in Haskell, you can. But again, in Haskell, the types, like in those other programming languages, don't stick around at runtime. They do get erased. So what's actually happening is that the compiler is implementing a type-directed translation of the program using the type information. So essentially, the compiler is saying, all right, I see that you're using empty. It's supposed to be an optional. I will replace it with empty on optionals, and then eventually that will get evaluated and it becomes nothing. Now, why is this interesting? Well, this whole detour is relevant because type classes are therefore compile time functions from types to expressions. And this is really interesting because this is kind of similar to what I was talking about with macros earlier, where macros are functions from expressions to expressions. Now we have compile time functions from types to expressions. So this might not seem that important, because if we just have empty and we're using it as a list, then we're writing that type annotation down, and it doesn't seem like we're really getting very much. But Haskell has type inference. So most of the time, you don't have to write the type annotations down. It just gets inferred. So in this case, Haskell is essentially figuring out that, OK, empty is a list here. Therefore, I'm going to replace it with empty on lists. Why does this matter? Well, because we have type inference and type erasure, and type classes, then we have these two worlds, expressions and types. And if we have type inference, then we have an automated mechanism from going from expressions to types. And because we have type classes, we have an automated mechanism from going to types to expressions. And this creates a genuine feedback loop. And we can actually use this to achieve code generation, which is fascinating, because this is not something that you can do very easily with a traditional macro system, because the type information just isn't there. In this case, we're generating code based on the type information that is known by the compiler about your program. Hopefully that made sense. So what's actually happening in this servant example is that there's a bunch of really horrible, hairy type class machinery that is picking apart this complicated type and translating it into expressions. And that's what's actually generating the server. So in that sense, there's sort of a similarity here between macro metaprogramming and type class metaprogramming. So what's the difference? Why would I want both? Why would I want both in the same language? How does one maybe do things that the other one cannot? So to give an example, consider the application of a macro. So like I was talking about earlier, macros are just functions from code to code. So a macro is going to take some expression. It's going to expand into some bigger expression. And this expression that is passed is going to end up somewhere in the output. But imagine that expression is just a variable, like x. The macro can't know anything about x, because it's just a variable. So it's just going to be treated essentially as a black box. So in that sense, macros are really good at local transformations, where you have something and it just uses the information that's directly passed to it. But this isn't necessarily true of type classes. If we have some definition of some variable x that's defined maybe in a completely different module, and then we apply show to it, which converts it to a string, and uses a type class to be able to convert different kinds of values to different strings, then it's still going to be able to figure out that, OK, even though that's in some other module, this is being applied to a list of integers, and it's going to use show on lists. And then by sort of inlining the definition of show on lists, we can see that there's actually another use of show in there. And so this process is going to happen again on that use of show. Now it's being applied. It's being mapped over that list of integers. So this is now going to be show on integers. And you can see how we get that feedback loop that I was talking earlier about, how one thing then sort of expands to another thing that then uses that type information, and we get that code generation. And so eventually we get this expression that converts that whole thing to a list. So to summarize, macros are really, really good at local code transformations. They're not allowed to look at other information about the things that are provided to them. But we do get custom syntax, because we're able to manipulate the code tree as much as we want, the syntax tree as much as we want. Type classes don't let us do that, but they allow us to use this rich world of information that's been made available to us by the type system. And this is really cool. And if you write Haskell programs, you see how, if you write Haskell programs and have also used Lisps, you can see how some of the DSLs in Haskell end up being richer than the things that you can write in a Lisp because of that information. So the question that I essentially had is, OK, we can have a language that has both of these two things together, and we can use them together. But can we get both in the same language feature? Can we write macros that essentially have access to that rich world of type information arbitrarily in a more flexible way than type classes can? So essentially, we already have functions that translate syntax trees to syntax trees. But can we also have functions that take a syntax tree and a type and produce a new syntax tree from that, where maybe that type is the type of the expression that was passed to it? So the answer is yes, but with some caveats. So in order to understand why this is hard, we have to first understand why implementing a language with types and macros is hard. So if we look at sort of an idealized version of a compiler, if you're a compiler writer, you probably hate me for just saying this is what a compiler is. But essentially, what happens in every compiler is that it's going to parse the program into some syntax tree, and then it's going to ship that off to the compiler, and that's going to be compiled to some binary bytecode. So if we want to add types to this compiler, well, that's just a stage in between, right? We parse the program, then we send it to the type checker. Once the type checker has said, yep, it's typed correct, then we send it off to the compiler. We end up compiling that program, do the same thing as before. It turns out that adding macros to a language is very similar. We start by essentially just inserting another stage in between where we parse the program, we find all the macros, we expand them, and then once the macros have all been expanded, we ship it off to the compiler. So a naive combination of these two things would just look something like this, where we put the expander in front of the type checker, we parse the program, send it through the expander, we get fully expanded code with no macros, therefore we can send it to the type checker checks the types, we send that off to the compiler, everything works well. But there's a problem with this. Can you see what the problem is? The problem is that the type checker only runs after macros have finished expanding. And that means that, by definition, the macros don't have access to types, because the types aren't going to be inferred until after the macros have gone away. So this produces what I have been calling Lisp-flavored Haskell. And it's not good enough to me. I mean, it is useful, right? You get macros and types in the same programming language, but they're sort of just thrown together. There's not this deep interaction between them that I would like to be able to get. So in order to have that, what you really need to do is interleave type checking and macro expansion. And this turns out to be very hard, and I did not come up with it. This comes from a paper that was presented a little less than 2 years ago at POPL called Type Systems as Macros. If you want to read more about sort of the general technique that Hackett uses, you can read that paper. And Hackett extends it and adds a whole bunch of additional things to it, like Haskell-style type inference and type classes and all sorts of things that you would want in a real programming language. But fundamentally, that's where the technique comes from. And the idea is that by interleaving these two things, by making it so that type checking and expansion are one and the same, then we can actually get type-directed macros. So to give some example of why we would want this and sort of interesting macros that we can write if we have this ability, this is one example of implementing GHC's typed holes as a macro, just as a library. And I didn't actually come up with this example. David Kirshenson, who's currently in the audience, was the person who came up with this and actually submitted a pull request to add it into Hackett. But the basic idea is that you can write to-do bang anywhere in your program, and it's just sort of a placeholder, and it uses the information in the type system to say what type is supposed to go here. And then it communicates that information to the editor in some way that it can display and say, hey, the first case, you need a string there. Then the second one, you need a function from string to integer. And the third one, you need an I/O action that produces an integer. And it turns out that implementing this in Hackett is not that hard. I'm not going to explain all of what this means. It's outside the scope of this talk, maybe someday. But essentially, it's a short macro, and you can do it. And you can actually get access to the type information using the macro system. So you can also do other interesting things, like instantiation. So GHC relatively recently added something called visible type application, which is essentially a form of explicit instantiation. This is not as fancy as that. They did a lot of really, really nice things. But this that required plumbing a lot of information through the compiler. This doesn't. This is just a library, just a short macro. Well, OK, short is a little bit of a lie. It's horrible. I would not recommend that anybody write anything like this. But it is possible to do. So clearly, we need to do some work on making this information easier to use. But it is technically possible. Now, looking forward a bit, I want to also show you a couple of examples of some really kind of more out there ideas that you could maybe implement with this, but you can't implement just yet in Hackett, because this is still something I'm experimenting with. So here's an example of maybe a macro that could be used to generate catamorphisms. Now, catamorphism is a fancy word that essentially just means a generalized version of fold. So if you look at the bottom one, it really is just fold on list, but it generalizes to other data types. This is something that's entirely mechanical that you can generate from the definition of a data type, but traditionally it's sort of obnoxious and you have to write it yourself. Theoretically, you could do that with a macro. However, not quite there yet. There's a few tricky details that if you're interested in hearing what they are, talk to me after the talk. Another example, maybe even more ridiculous, is maybe we could create a macro that allows you to query from a table using SQL, and it uses the expected type of what it's supposed to return to bind variables that correspond to the column names in the table. Maybe people think that's ridiculous and a horrible idea, but I think it would be cool if you could implement something like this just to see if it worked. So anyway, that was a lot of information that I threw at you all at once. But to recap, to summarize, Hackett is a Haskell extended with macros, and this gives us nice things. It lets us extend the language without having to modify the compiler. It lets us eliminate boilerplate. It lets us build nice DSLs with custom syntax. Macros allow us to augment the metaprogramming facilities already provided by Haskell. It does not replace them. They work together in a nice way. And type-directed macros are theoretically available. The interface needs to be a lot better than it currently is, and there's still a lot of work to do there. But it's something that, because of the interleave type checking and macro expansion, is something that is possible in Hackett, whereas it's just completely out of the question in most implementations of this sort of thing. And that's it. Any questions? All right, I am looking at Slido at the moment, and there's one question there right now, which is how does the presence of macros affect decidability of the type system? Well, so it's very much, because type checking and macro system, and macro expansion are one of the same, and macro expansion is already undecidable. You can write arbitrary functions. The type system is obviously undecidable as well. The type system itself, I guess, isn't necessarily undecidable. It depends on how you kind of define it. I think that there's a lot of work that needs to be done to sort of theorize, come up with a model for what some of these things mean. What does it mean to have a macro system conjoined at the hip with a type system? It's not something that has been extensively researched, but it's something that I'd be interested in doing. Haven't done that yet. So maybe not a super satisfactory answer, but that's all I can say. All right, so one other question. What does Hackett get us that template Haskell doesn't? That's a good question. I anticipated that it would be asked, so I actually have a couple of slides. So this is a question that I've been asked a number of different times before, but I haven't really had a great explanation for it in the past. This time I do. So the basic difference between these two things is the idea of macros versus splices. So some people would say that template Haskell is a macro system. I would disagree, but it is ultimately kind of a fuzzy definition. But what I think of as a macro is something that transforms code to code. It has this type that I talked about earlier. Template Haskell doesn't have this. It has splices, which are functions that produce code. And they are run at compile time, but they don't take code as input. Why does this matter? Well, if you look at the application of a macro, like this def server thing, it's able to have any custom syntax it wants. A splice is just an ordinary function that runs at compile time, so it has to still conform to the syntax of Haskell. So if you wanted to encode that same thing on the top in template Haskell syntax, you would have to write something really explicit on the bottom, which works OK in this really simple example. But when you have really complex macros with optional pieces to them and fancy grammars, you really can't encode the things that you would do with macros using a splice system. But that's not all. It turns out that this type signature is actually a little bit of a lie, because in template Haskell, that AST that gets returned can't also contain splices, which means that you have a really limited system where there can only essentially be one layer of splice transformation, and then everything has to stop. That's really limiting in terms of what you can do. But that's not all either. It turns out that GHC has a stage restriction, which basically says that if you define something in the same module and then try to use it at compile time, you can't. They have to be in different modules. Sometimes this is awkward if you end up with kind of cyclic dependencies, and it's awkward to break them up into two modules. Also, you can't define a function or define a splice in the same module where you use it, which might not sound like a big deal, but then when you end up doing really fancy macros, where you have macros that define macros and then you use them, it sounds ridiculous, I know, but it is actually useful. That doesn't work with this kind of system. But that's not all either. It turns out that, or first of all, Hackett handles that. It turns out that template Haskell also imposes various constraints on expansion orders. So basically what happens is when you have two splices at the top level of a program, imagine make some data type is some function that basically defines a data type in terms of, that has a field of the second argument here. So we're defining a data type called foo that holds a bar, and a data type called bar that holds a foo. Normally, that would be totally reasonable to do in Haskell. Doesn't work in template Haskell, because the way template Haskell works is it basically just takes all of the splices, it chops up your file into chunks, and then it type checks them individually. And this causes problems, because if you have two things that refer to each other, it doesn't work. And if you end up having to have a situation where you want to define something that's mutually recursive, you're kind of stuck. Hackett handles that fine. So there's a long list of differences between these two things, and they really are designed to do totally different things. Template Haskell is not bad. It's just designed to do something simpler than what Hackett is designed to do. It's very useful. I think writing Haskell without template Haskell would probably be kind of painful, but it's definitely it's a different thing. All right. Let's see. Other questions. List macros are easy in part because the AST is nested lists. What's it like manipulating the AST of Hackett? Well, Hackett has Lisp syntax for a reason. And indeed, if you say, look at the definition of the expression in Haskell, this is the actual data type that doesn't fit on the slide. In fact, it's really big. This is just for expressions, by the way. This is not the whole syntax tree. This is really hard to manipulate with macros for precisely that reason. It's very difficult to predict what a particular sequence of characters will translate into in the AST, and that makes it hard to write extensible syntax. With Hackett, just like in any other Lisp, it's just built out of lists, identifiers, and strings, and it's not any more complex to manipulate than it would be in a traditional Lisp. Hackett does have sort of infix syntax, but it's designed in such a way that that just desugars down into the prefix syntax, and it's always explicit, so it's not difficult to parse. It's a good question. I still have, yes, I still have some time, because I intentionally left a lot of time. All right, so let's see. What would it take to use Hackett at phase 1? That's a very Racket-specific question. If you're not familiar with Racket, phase 1 essentially means at compile time. So what would it take to use Hackett to write macros is essentially the translation of that question, I think. Sorry. It's OK. It's a good question. So theoretically, nothing prevents you from writing your macros in Hackett itself. So for a little bit of context, the macros that I've been defining in Hackett, I've been using Racket to write the macros that then expand into Hackett code. So it's a dynamically typed macro definition language. That is mostly just because I haven't gotten around to implementing like the bindings, the types for what it means to have typed syntax transformers. There's no like fundamental reason that can't be the case. It's just that I haven't gotten around to implementing it. And because Racket has a lot of really, really nice pattern matching facilities for handling syntax and creating macros that would be a non-trivial amount of work, but maybe not any new research per se to implement in Hackett. So there's nothing theoretically that prevents it. It would just be some programming. Let's see, a few more questions. So macros can generate expressions. Can they generate types, patterns? Yes. And yes, those are both things that Hackett supports. Is the compiler / runtime new from the ground up, or are you reusing parts of existing compilers for each language? It's a good question. The way that Racket works is it's designed for essentially adding new languages. GHC is not. So I'm reusing a lot of Racket. I'm reusing the Racket macro system. I didn't re-implement all that. I did have to re-implement all of the GHC type system. That's unfortunately too different to really reuse, and again, it's not really designed for that sort of thing. Racket is. So I'm reusing a lot of the runtime support from Racket. I'm reusing the macro system. I'm reusing their pattern matching system right now. I'm reusing the whole VM and runtime that they use. But all of the sort of type checking stuff is all new and built on top of that. So that's a lot of questions. There's a few more. I think I'm going to let people come and talk to me after the session about those things instead of forcing everybody else to listen to them. But by all means, do so. There's still a bit of time before the closing keynote, and thank you very much.